Welcome back. So again, what we were just talking about is part C here, and we're actually looking to use the central limit theorem. And to be able to do that, we have three conditions that have to be met about the problem. And then what's the distribution of the sample mean, and then specify the model and mean and the standard deviation. So again, let's take a look at that. So the three things that we must check are the randomization condition, the independence assumption, which again, that deals with your 10% condition. And then we have to check to see if it's large enough sample and check that condition also. So first thing, you're assuming that the 60 women from the doctor that the doctor's treating are considered representative of the sample of all pregnant women, and that um, one pregnant woman versus another pregnant woman are definitely independent of one another, and that they are selected randomly. And then likewise, one being pregnant is not dependent upon another person being pregnant. So it is reasonable to think that the durations of the patient's pregnancies are mutually independent. The 10% condition, since 60 women and the doctor is treating, certainly definitely represents less than 10% of the population of all women. And then the large enough sample condition, the 60 women is large enough. In this case, any sample would be large enough since the distribution of pregnancies is normal. And again, that normal part was given to us, so we are allowed a large enough sample. So, since this is met, we are allowed to use the central limit theorem. And the mean duration of the pregnancies, which was mu, was 266, with a standard deviation of 16. So again, those are the things that they had asked for. And since the distribution of pregnancies durations is normal, we can model the sample distribution of mean pregnancy during a normal model, with mu is equal to 266 days, and the standard deviation is equal to, now remember this deals with this one here, so we're not given the probability, remember, like probability of success. So this is a quantitative data, so we're using sigma divided by the square root of n, which is 16 divided by the square root of 60, because there were 60 women, and that is equal to 2.07 days. This 2.07 days is the standard deviation, which we will be using in the next part, part D. So what's the probability that the mean duration of these patients' pregnancies will be less than 260? So again, think of your normal model. What does that look like? 266, where is that? That's your mean. And then where's 260 compared to 266? You see that's less than, so it's going to be to the left of 266. In fact, it's very far away, standard deviation wise, it's very far away from the 266. So let's take a look at again what the probability, what's the probability that the mean duration of these patients' pregnancies will be less than that. So here's what that looks like. So again, here's your model. You have your normal model here. There's your 266. And again, way to the left, 260. So how do we figure that out? So you have to, again, use your z-scores. So you have p hat minus p divided by the standard deviation. This is just another way of saying y minus mu divided by sigma. There's your p hat. There's p. There's your standard deviation. So you have your 260. This is the one that we're looking at. There's your mean. And there's the standard deviation that we just found. So 260 minus 266 divided by 2.07, again, this is going to give us a negative number, is negative 2.899. So now this again is that number for our z-chart. We looked that up using our z-chart, and negative 2.899 in our z-chart gives us a number of 0.0019. So now we write this is our answer. So now we write a sentence, what that answer really means. So according to the normal model, the probability that the mean pregnancy duration is less than 260 days is 0.002. Okay, so that's that type of problem. And then let's move on to another type. So here's one more. Suppose that about 13% of the population is left-handed. A 200-seat auditorium has been built with 15 lefty seats that have been built in, that have like a built-in desk on the left side rather than the right arm of the chair. In a class of 90 students, what is the probability that there will not be enough seats for the left-handed students? All right, so let's take a look at how to solve that. So here's our plan. I want to find the probability that in a group of 90 students, more than 15 will be left-handed. So again, we have to figure that out. What is that percentage? So since 15 out of 90, and that's again just divide, is 16.7, I need the probability of finding more than 16.7%. And that 16.7% is the left-handed students out of the sample of 90. If the proportion of lefties is indeed 13%. So this is our kind of plan of how we're going to deal with that. So are we allowed to use the normal model? Well, it doesn't say that we are using a normal model or if it is distributed that way, so we have to check. So the check conditions for using a normal model, again, are the randomization condition, the 10% condition, and the success failure condition. So let's go ahead and through those. So in the randomization condition is there's 90 students in the class, and they can be thought of as a random sample of the students. So the students that are sitting in the class are randomly sitting in there, and they're randomly sampled. And we can assume that. The 10% condition is 90 is less than 10% of all the population of students. And that is an assumption, again, that we can use of the school. And the success failure condition, again, is NP, N is equal to 90. P is the probability of that was given to us, and that was 13. And that comes out to 11.7, which is indeed greater than or equal to 10. And then NQ, so you have your probability in the failure there, is a 1 minus P is 90 times 0.87, and again, this is definitely greater than or equal to 10. Therefore, we are allowed to use the normal model. And I'm going to, again, pause here. My time is nearly up for this, so I'll pause here and we'll come back.